As a very fast recap of what I've talked about in the previous videos, we talk about two types of supervised learning. We talk about regression, where we learn the relationship between a dependent variable and independent variables to predict numerical values. And we talk about classification, where we instead learn to predict the category to which new data belongs. In this third learning video, I will talk about two supervised learning algorithms, decision tree and random forest. Decision tree is a model I think you already have heard about. So it's fairly easy to follow a decision tree, apply it to new data to make predictions also manually, as long as the tree is not too deep. So what happens when we learn a decision tree from data is that we learn rules that create branches in a tree. And we do that using the CART algorithm, classification and regression trees algorithm. Suppose you want to make predictions of whether or not it would be profitable to release a partly tested feature. So this is about the question of when to stop testing. And let this feature be represented by two variables here. On the x-axis we will see some type of code coverage, and on the y-axis a criticality measure of this feature. And then let the data look like this. So the green dollar sign here shows that in the past it was profitable to release a feature like this, and the red symbol here shows it was not profitable. So to learn a decision tree from this data, it would start with having all data points here in the root node of the tree. And the root is actually on top here. So this is a top-down approach that starts with the root. So the tree will grow upside down here. And we will continue to create branches in our tree until we have only one type of data in the leaves. That works for this fairly simple example. So what we do now, the first level, the first question, our classification CART algorithm here will ask is, what is the most discriminating rule I can come up with for one of the features? And that means the best way to separate two types of data here. And what the algorithm will find here is that this rule here would be a good ID, because everything here to the right, 6 data points, are of the type green dollar sign, so profitable to release. And this we can then represent as a rule. In this case, coverage is greater than 0.55, and then we apply it to the data, and it looks like this. And what we see now is that in this branch here we need to do something. In this node we have two types of data, so we will do the same thing again. We will look for the most discriminating rule for our features, and the algorithm will find this line here, and everything above this level is non-profitable. Here in this example we turn it into a rule, and we apply it to the data, and it looks like this. And then we have a node here with two types of data, and we do it again, and we find this rule. We turn it into a rule like this, coverage greater than 0.4. So now we again used this coverage variable here to create a rule, and that is for sure allowed. And then we apply this to our data, and this is how we can create a decision tree using the CART algorithm. So if we have a new feature now under test, and we want to make a prediction of whether or not it would be profitable to release this partly tested feature, the first question we would ask, according to this tree, would be if the coverage of this feature has been greater than 0.55. So when is this a good algorithm then? Well, if you need human interpretable rules, this is the machine learning algorithm for you. It doesn't get easier than this, and as I said, if as long as the tree is not too deep, you can also manually work with this for your input data. Random forest is related to decision trees. So the idea is, okay, if it's such a good idea to learn a tree from the data, why not learn a whole bunch of them, make them slightly different, and let them vote together in an ensemble. And this is the idea with the random forest, and this leads to a more robust model. And I will now again show you the same example here with whether or not it would be profitable to release a partly tested feature represented by coverage and criticality as the two variables here. And now this is how you learn an individual tree in a random forest. So just as before, you would start with all your data in the root node. And in this example, instead of just looking at these two variables I presented, we will have a whole a bigger set of variables here. 9 in total. It's not too important what they are, but they are different here. And what you would do with a random forest approach would be to randomly select a subset of these independent variables here, and then for only these three uh, independent variables in this example, the actual number of independent variables selecting the subset, that's a parameter, but it is a subset, and for these variables in the subset you would find the most discriminating rule. So in this example, let's say it's the branch coverage here, and then you would apply it to your data. It would look like that, and then in the next level in your tree here, you would again randomly select a subset, and then you would, for these three independent variables, select the most discriminating one. And let's say for the number of commits, you could come up with a really discriminating rule for this data, and then you apply it, and then you on this level also randomly select, and you in this example find that the lines of code was the most discriminating one, and you apply it to your data, and here you have a tree, an individual tree in a random forest. And then you would repeat this and do it multiple times. A rule of thumb I've seen is to have between 64 and 128 trees in a forest, but this could be also a much higher number if that works better in your specific application. So when is it more promising to use a random forest approach? Well, it's often fairly easy to use. There's limited tuning involved. Often it works fairly well just out of the box. You can try it without putting too much effort into it. It is fairly interpretable, and it gives you some insights into the feature's importance as well. But if you have a very deep tree or a big forest where each tree is very deep, then the predictions might actually be fairly slow. But if you can live with that, then random forest is surely an approach to try out. By that, I want to say thank you.